This sample demonstrates how much power and how much authority the pointer can give to a program. Basically, what is happening in this little sample is that function square is capable of accessing objects outside of its local scope. Initially, it starts with just its parameter and using it inside an expression, but indirection facilities that are built into the language allows it to access objects outside of its scope, because of course while this function call is in progress and this function is still executing, everything freezes inside main, and so a variable x is in scope, it's safe, it's just waiting for this expression to finish. And of course, as a result of it, if you want to print x right here at this stage, it is guaranteed that x will have new value 25, which is a square of 5. So this was a demonstration of using pointer not as a standalone variable like on this slide, but rather using it as a parameter of a function. So why use pointers? Pointers provide indirect access to other variables and to other objects. So we already discussed the meaning of an asterisk in front of the pointer, so that you now understand how this operator works. And this is the discussion of pointer dereference. Again, asterisk and ampersand are the two operators that are often used with pointers, but with just one warning here. Just realize that asterisk used inside a declaration, here's the declaration of the variable which happens to be function parameter, whenever the pointer, whenever the asterisk is used inside a declaration, it is a type modifier, and this is not a pointer dereference operator. This is just a type modifier. It is only when the object already exists then an asterisk becomes an operator which dereferences the pointer. Let's just highlight of this slide. Right, so this is a summary of various uses of pointers. To initialize the pointer by taking address of another object, to declare pointers of different types, and eventually we can dereference the pointer to be able to access finally the value which is pointed by the pointer, or which address is stored by the pointer. Pointers have a close relationship with string literals, or literal strings. So literal strings look like this. Basically, we're talking about things that we enclose in double quotes in our program. So these are literal strings. Literal strings are always stored as individual characters. Right? So whenever compiler is seeing this string of characters, it is allocating as many characters as necessary to accommodate the characters, and then it also automatically appends a null character. Null character is a character which has all bits set to 0. Typically it's written as, if you want to use character literal with single quotes, it's written as single quotes with backslash and 0 indicating the actual value of a character, not its printable value, but rather the internal value stored by the byte, which is accommodated by this character. So this is called null character in situations with string literals. So string literal returns back the address of the first character in memory. Basically what happens here is this hello string, what it does, step number one, it allocates space for characters, appends 0 characters. So notice that hello contains 5 characters, and the 6th character is also allocated to accommodate the 0 terminating character. And it returns some sort of address, the address of the first character of this string. So the address indicates location of the first character, and the 0 terminating character or null character tells where the tail of this sequence of character is when we try to process it. So when you want to capture the address of this character, naturally you would use a character data type and a pointer and give that pointer a name, and that pointer will remember the location of the first character. Let's try an example with this. The way it's written is char asterisk p hello equals hello. And unfortunately it will no longer compile correctly. The reason for this is that when we try to compile it, these characters are allocated in a constant memory, in memory which is read-only. And having a pointer that is a pointer to any sort of character, unfortunately will cause compiler to give us an error that will say, let's actually try this. Just build this. It says cannot convert from constant array of 6 characters to a pointer to a character. So what it needs is just needs us to specify more explicitly that we promise that this pointer will not attempt to change any of these characters, because I already told you that these characters are actually sitting in read-only memory. That is the rule, that every string literal is not modifiable. Once allocated, it just sits in global memory and is safely placed in read-only segment of memory. So for this reason, we need to actually provide more modifications to the type of this pointer when we deal with string literals. We have to say const. Const is like a magic word in C++ that improves safety, improves performance, improves compiler ability to optimize our programs. Because every time we use this keyword, which is a magic keyword to make your code run faster and be safer, it will apply a lot of different rules to optimize your code, to make your program safe, and so forth. So this is actually very good at every opportunity that we can use this const keyword. We should remember to use it, and this time the compiler is actually forcing us to use this when we have a string literal which is allocated in read-only memory and we want to have a pointer that is using it.